Hello, my name is Miguel Jara Maldonado and I am one of the authors of the work entitled A Multi-Resolution Machine Learning Technique to Identify Exoplanets. Did you know that it has been statistically speculated that each star in the Milky Way could harbor at least one exoplanet? This means that there should be more than 100 billion exoplanets in the Milky Way. So far, only nearly 4,000 exoplanets have been found in the entire universe. In this video, I will explain to you how my colleagues and I have attempted to aid in the problem of discovering new worlds with the use of machine learning and multi-resolution analysis. For this purpose, I will first introduce you to the exoplanet topic, including an explanation of one of the most popular exoplanet detection techniques. Then, I will explain you the challenges faced within this area. Later, I will be talking about our exoplanet identification proposal, showing you the results that we have obtained following this proposal. And finally, I will draw conclusions. An exoplanet is any planet found outside the solar system. Its name comes from the abbreviation of extrasolar planets. There are several reasons why it is important to study them. But in my opinion, the most important ones are extending our understanding of the universe and ourselves. Is the solar system a typical stellar system? Are planets like Earth common? How do planets form? Also, studying exoplanets opens the possibility to look for habitable planets and to look for life outside planet Earth. One of the techniques used to discover exoplanets is the transit method, which has been used to discover a great number of exoplanets. A transit event is very similar to a solar eclipse. In a solar eclipse, when the moon passes between the Earth and the Sun, the light of the Sun is blocked and everything gets dark. Similarly, when an exoplanet passes between the observer and its host star, the light of the star is received dimmer. And this is called a transit. Transits can be studied by analyzing light curves, which are light intensity values recorded over time. As it can be observed in this slide, real light curves are not as easy to interpret. While the transit signal can be seen as a valley in the light curve, there are other sources that may be confused with it. For example, stars may have dark spots that are observed while they rotate. This type of stellar variability is pretty common and it may cause confusion. Other sources that may lead to false positives are pulsations and eclipsing binaries, amongst others. Light curves are time series that commonly contain discontinuities for several reasons, such as the relocation of an observing satellite. Also, some transits may be hidden by noise, causing ignored transits in the existing light curves. In addition to this, the hardware limitations of the observatories is a great challenge for every of the exoplanet detection techniques. Another challenge in this area is the quantity of data to be analyzed. The Kepler satellite observed more than 150,000 stars in 4 years. The observations stored account for nearly 3 million files. There is more than 1 terabyte of information recovered by Kepler. However, the Kepler satellite did not cover a big area in the sky. If you take a look at the starry night, you may want to look for the Cygnus constellation and note that it is not as big as other constellations. The field of view of Kepler did not even cover the entire size of this constellation. What would be the quantity of data to be processed if we summed all the data from the current observatories that have been used for exoplanetary science? So far, I have shown you several challenges that difficult the exoplanet discovery. This is why the use of machine learning in this area is important, especially when addressing big data that has to be processed. We have previously proposed the following exoplanet discovery pipeline. First, the data is acquired. This implies using real observatory data, but simulations may be used too. Next, the light curves obtained have to be preprocessed. This allows one to remove noisy signals such as stellar variability. Look at how by preprocessing the light curves from the top, it becomes more obvious that there is only one transit in this light curve. The next step is detecting a transit signal. This involves spotting periodic signals that could be explained by an exoplanet transit. Finally, it is necessary to determine if the detected signal was really caused by an exoplanet or not. Machine learning may be used in the last 3 steps of this pipeline, but in this work we have focused in the identification step, which is also called signal vetting. We propose the use of 2 multi-resolution analysis techniques. The first one is called empirical mode decomposition. Suppose that you have an X signal. To obtain the intrinsic mode functions, the first step would be to form the upper and lower envelopes of the signal by looking for its maxima and minima. Next, it is required to average these envelopes to obtain the mean. Subtracting the envelope mean from the signal would result in a possible intrinsic mode function. If this function satisfies 2 conditions, the intrinsic mode function is then stored. These conditions are that in the whole dataset, the number of extrema and the number of zero crossings must be equal or differ at most by 1, and at any data point the mean value of the local maxima envelope and the local minima envelope is 0. The other multi-resolution analysis technique that we tested is the Ensemble Empirical Mode Decomposition. This technique requires to generate several signals by adding white Gaussian noise to the original X signal. Then, the intrinsic mode functions are looked for as with the empirical mode decomposition technique. Finally, all the intrinsic mode functions of each mode are averaged to obtain the final intrinsic mode functions of the signal. Each intrinsic mode function will represent a different mode, starting from mode 1 to the last mode found. This is where the details of the signal will show up, because each mode will contain a different level of resolution of the signal. We used 2 datasets with simulated transits and different noise models. Then we applied the empirical mode decomposition and ensemble empirical mode decomposition techniques using 10 different modes. And we tested the performance of different machine learning models using each different mode and the light curves without preprocessing. The models that we tested were 4 configurations of the k-nearest neighbors, the ridge classifier, a random forest, and a convolutional neural network. Finally, we compared all the results in terms of accuracy, precision, specificity, recall, and execution time. The 2 datasets that we used are composed of 10,000 light curves that have 15,000 data points each. The difference between them is the base light curve to which the simulated transits were added. The first dataset, called the real light curve dataset, was created using real light curves extracted from the Mikulski archive for space telescopes. The light curves chosen were those that contained periodic signals marked as non-transiting planets in the 24th Kepler data release. These light curves were detrended by using splines. Then, the transit simulations were added to half of these light curves. The Batman transit model was used to simulate the transits for both datasets. The second dataset used, called the 3-median dataset, was created by using the simulated noisy photometric data model shown in this slide, where F-transit is the transit generated by the Batman model. A is the amplitude of the simulated stellar variability. Omega is the period of oscillation. Phi is the phase shift. And N is a Gaussian distribution used to generate random numbers with a mean of 1 and the standard deviation of the normalized radius ratio between the planet and the star over a sigma tolerance noise parameter. Then, the simulated transits were added to half of these light curves. Finally, a 3-median filter was used to detrend these light curves. Once that the light curves were generated, the folding and binning processes were used. During the folding process, the original light curve is folded to center the transit event. This enhances the transit signal and also provides a geometry that is easier to identify by the machine learning models. After folding the light curves, the binning process was used to set the length of all the light curves to 2048 data points. The binning process consists in reducing the size of the data by averaging all the data points contained in each bin. Finally, this is the slide that shows the 10 modes obtained after preprocessing a light curve with multi-resolution analysis. From top to bottom, the first to the 10th mode are shown, both for the empirical mode decomposition to the right and to the left, the ensemble empirical mode decomposition techniques. These are the results obtained with one of the two datasets. The blue bars represent the accuracy of the models without pre-processing the light curves. Then, the orange bars correspond to the results using empirical mode decomposition, and the gray bars the results using ensemble empirical mode decomposition. It can be observed that in most cases the accuracy is improved by using any of these two techniques. This other graph shows the results obtained with the second dataset. In this case, the performance of the k nearest neighbors models is noticeably increased using multi-resolution analysis. We attribute the improvement of performance to the fact that using multi-resolution analysis allows one to enhance the transit signal, attenuating the noise signals. This helps to make the models more stable when looking for exoplanetary transits in different datasets. Also, the convolutional neural network obtained 99.32% accuracy, which is the best result that we have obtained so far even compared to our previous work. Recall that we tested each model using different modes of the empirical mode decomposition and ensemble empirical mode decomposition techniques. In these figures, the different accuracies obtained using each of the different modes are shown. For both datasets, the best results were obtained within the 5th and the 10th modes, with a higher concentration of best results near the 6th mode. This is also the case for the ensemble empirical mode decomposition, with the exception of the convolutional neural network, which obtained its best result in one of the datasets within the 1st mode. We conclude that empirical mode decomposition and its ensemble variant are very helpful for improving the performance of the machine learning models tested in terms of accuracy and execution time. This is because these techniques have allowed us to reduce the influence of noise in the light curves, which enhances the transit signal, facilitating their identification. Another advantage of these techniques against other multi-resolution analysis techniques, such as the discrete wavelet transform, is that the signal is not downsampled. Downsampling may limit the possible configurations of certain models, such as the convolutional neural networks that have pooling layers that perform downsampling between layers. Finally, with our results, we have proved which are the most useful modes to preprocess light curves using the empirical mode decomposition and ensemble empirical mode decomposition techniques. There are many exoplanets to be discovered, and the use of machine learning may accelerate this process. For this reason, we will continue to research how to create helpful tools for astronomers to use in this area. Finally, I want to thank you for your attention, and I am looking forward to listening to your comments and answering any possible questions that you may have.